Yeah, hello, hello, hello. I believe that by now it's okay. Yes. Excuse me. I'm listening. See if everything is okay now.
Medicare Foundation is aimed.
All right. So yes, I think we are having issue with sound, but we are trying our best to get things done so that we can start today's section. So kindly permit me just a few minutes, then we begin. So we'll be looking at we'll be looking at geophysics, principle of geophysics. Yes, that's what we'll be looking at. Principle of geophysics. All right, so we are going to start with refraction and reflection of seismic waves, and I'm going to take you guys through it. So without wasting my time, now we have to look at. Okay, so just a minute. Then we begin. Now we are here. We are our concentration is going to be on seismic waves, seismic waves. Now, first of all, we need to understand what these waves are. So these waves, just like any other waves, obey. So they obey the laws of reflection and refraction. So just as light, light waves to obey the laws of reflection and refraction. In the same way, um, seismic wave also does so. Now, when we talk about seismic wave, we have two types of the seismic waves. That is the P waves and the S waves. But here we are not going to go into details into that because our focus is seismic refraction and reflection. So, what are the laws of reflection and refraction that POB? So, when we have a seismic waves encountering, let's say, a surface, and let's say the wave is from here, it hit this boundary, and there is acoustance impedance difference, then there's going to be a form of refraction, right? Now we are saying that it obeys the laws of reflection in the first place because when it is reflected, the angle of incidence will be equal to the angle of what? Refraction. Do you get it? So we know the laws of reflection. The laws of reflection. One is that angle of incidence, angle of incidence is equal to angle of what? Of refraction. Then the second law of reflection. So we are looking at this is reflection. Let me get this red marker. So this is reflection. You get it? We are saying that seismic waves will be this law of reflection. So the angle of incidence will be equal to the angle of refraction. Then the second law, so the incident ray, the incident ray. So what is the incident ray? The ray that is coming from the source of the wave. So this is our incident ray. So the second law is saying that the incident ray, the reflected ray, and this perpendicular line, we call it our normal incident ray, reflected ray, and the normal at so this point we are calling it at the point of incidence. At the point of incidence, they all lie in the same plane. Lie. Let me erase it. They all is point. They all lie in the same plane. So we are saying that seismic waves would obey the laws of what? Reflection. Then it will also obey the law of what? Refraction. So when I have two boundaries, let's say boundary A, boundary B, and let's say this is my normal, and a seismic waves is entering. Now boundary A has a density rho A, boundary B has density, or layer, sorry, not boundary, layer A, layer B. Layer A has a density A, layer B has a density B. Because assuming layer A, the density of layer A is not equal to density of layer B, then there is what we call optical density difference. Optical density difference. And when this happens, then if this is the seismic waves or seismic waves entering from this layer, entering this layer, it's going to be what? Refracted, either to this direction, or it will move away, from the earth, from the normal. So these are the laws that we are going to deal with. So we are going to look at it in different form when we have um, a seismic wave passing through different words, different boundaries. So let's start. So If I have a layer of rock, it's a layer of rock, and there's another layer of rock, right? So this is layer A, layer B, and this is my source of what? This is my source where I'm going to produce my seismic waves. Now, layer A has density, let me call it rho A, and layer B has density rho what? B. So density rho A and what? Rho B. Now, because they have different density, the seismic wave will travel with the speed of the layer. Now, when we talk about seismic wave, it does not have its own velocity, or let me say speed or velocity. It does not have its own velocity. It takes the velocity of the layer or the medium it's traveling through. So if a seismic wave is within layer A, the speed that it will use to travel is different from the speed that it will use to travel in layer B. Do you get it? Provided the two layers are what? Different. If the two layers are different, it means that they have what? Different what? Densities. Do you get it? So let's take the case of refraction. Now, for refraction to occur in seismic waves, there must be what we call acoustic impedance. Acoustic impedance. Do you get it? Without, if there is no acoustic impedance, then there's not going to be any what? Refraction. So, sorry, reflection. So, there is an acoustic impedance between layer A and layer B. And so when the wave comes this way, it's going to be what? Reflected in this direction. And in that case, the velocity of this wave here is going to be the same velocity of this wave here. So this wave, because the wave is traveling within layer A, they are going to travel with the speed of what? Of layer what? Layer A. Now, in situation where there is refraction, so let's take for instance the refraction situation. This layer A, this layer B. Now we are going to look at case 1 of the refraction, where density of layer A is greater than density of layer B. Now, in seismic or seismic wave, if you have a bigger density, if your density is big, your velocity will also be what? It's also what? Big. Why are we saying that? If you remember this equation for primary waves is equal to square root of k plus 4 over 3 mu over the density. And we said that the density is a function. It's a function of k, that is bulk modulus and rigidity modulus. So if this increases, although mathematically the velocity is supposed to decrease, but because if the density increases, the bulk modulus and the rigidity modulus will also increase. If a body has a bigger density, then the velocity of the seismic wave traveling through it will also be what? Be big, right? So that point has been made. So in that case, in this equation, the velocity in medium A and the velocity in medium B. So if this is our first case, density of medium A is greater than density of medium B. And so if that happens, means that the velocity of medium A will be greater than the velocity of medium B. Do you get it? Now, if the velocity of medium A is greater than the velocity of medium B, then we say that medium A is what? Dense, and medium B is what? Less what? Dense. Do you get it? All right. So what will happen during what? Refraction. So let me change the color. Let's see what will happen during refraction. So when the wave comes and hits this point, in this case, the refracted wave moves towards the normal. So under normal circumstances, the wave is supposed to continue in this. But because there is density differences and there's going to be a change in velocity, the wave moves towards the normal. So let me call this normal. So that is the first case. So the first case is when the layer A and layer B, and the wave is from layer A, and layer A has a greater density than layer B. So mean that layer A is dense than layer B. And so the velocity of what? Layer A will be greater than the velocity of layer B. So when refraction occurs, the refracted ray, so this is the incident ray, is the refracted ray. The refracted ray will move towards what? The normal. Now let's look at the case 2. Let's look at case 2. So case 2 is the situation where layer B density, or the density of layer B, is greater than the density of what? Layer what? A. So let's draw our layers. This is layer A, this is layer B. Now, if the density of layer A is greater than the density of layer B, the wave will travel in layer B with a certain velocity, Vb. The wave will travel through layer A with a certain velocity, Va. Now, since the density of layer B is greater than the density of layer A, it means that the velocity in layer B will be greater than the velocity in layer A. So in that case, this will happen when there is refraction. This is what will happen. The wave will come under normal circumstances, it's supposed to continue in this direction. Now, because layer A is less dense and layer B is denser than layer A, and the velocity in layer B is greater than the velocity in layer A, the wave will move away from the normal. So this is what I call the normal. So this is the incident ray. This is what? The refracted ray. Now, in practice, we always want a situation where the layer below are denser, so that the wave can come up surface. So you see, when we are in the field and we are doing seismic refraction or seismic seismology, and we connect our focus here and we connect our geophones, we want the wave that we are going to send down to come up. So assuming case 1 was the what happened, then the wave will be moving away from or moving towards the normal. So there is no way the wave is going to come up. But when we have a situation where the layer beneath are denser than the layer above it, then we are going to have a possibility of the wave what coming up. You get it? And we need the wave to come up for our geophones to pick these waves doing what? Seismic refraction. Are we okay? All right. So we will look at case 3. Let me claim this and look at case 3. Case 3. So I'm still building things up. So case 3. So case 3. Case 3, we have the situation also where the density of layer B is greater than the density of what? Layer A. Right? So let's draw our boundaries. This is our boundary. This layer A, this layer B. Let's pick this to be our normal. right? The velocity of what? Layer A is here, velocity of layer B is here. Now, because the density of layer B is greater than the density of layer A, means that velocity of layer B will be greater than velocity of layer what? A. Now, here comes a situation. The incident ray comes like this at a certain angle, theta, under normal circumstance is supposed to continue in this direction. Now, in this case 2 is supposed to happen. The refracted ray is supposed to move away from what? From the normal. That's our normal. But in this case, the refracted ray moves along our boundary. So this is the second case. In that case, our angle of incidence, we call it the critical angle of incidence. So this is angle of incidence. You get it? The angle between the normal and the ray. So that's how each of the angles are. So in this case, this will be our angle of incidence, and this will be our angle of refraction, the angle of incidence. But in this case, case 2 condition is in play, but the angle, the angle of the incident ray is incident at a special angle, and when it's incident at a special angle, it causes the refracted ray to move or to be refracted along the boundary between layer A and layer B. In that case, the angle of refraction, theta r, the angle of refraction is what? 90 degrees. And we know for refraction, the Snell's laws works. So sine angle of incidence over sine angle of refraction is equal to velocity in the first layer where the incident ray can be found over velocity in the second layer where the refracted ray can be found. So in this case, we have sine theta I over sine theta r is equal to V A over what? V B, right? But we know that theta r is what? 90. So we have sine theta I over sine 90 is equal to V A over what? V B. And so we can say sine 90 is 1. So we can say that sine theta r is equal to V A over what? V B. So that is the first equation that we need. Now, just as initially I said that in seismic refraction, in terms of our applied geophysics, where we will go to the field, we plan focus, we plan geophones, and we do seismic refraction. We always want the refracted ray to come up so that, or to come to surface, because we send the waves subsurface and we are expecting the waves to come to surface so that the geophones at the surface can pick it. So if there is a case where the underlying layers are less dense, then it means that the refracted wave will move towards the normal, just as we saw in case 1. And if the refracted wave is moving towards the normal, it means that it is moving away from the boundary and it's not going to come up. We get it. But in case 2 and in case 3, we are seeing that the underlying layers are denser, and so the waves that are going to be refracted are going to the waves that are going to happen in these layers are going to move with higher than velocities. You get it? And so, yes, they are with that, the rays are going to move away from the normal, that is towards what? The boundary. Now, in this case, in case 3, when the wave does that, and to move along the boundaries, it's going to cause some form of vibration, and create this wave front. Now, when these wave fronts are created, it causes the some of the waves to be refracted to the surface. So, assuming this is the surface, it causes some of the waves to be refracted to the surface so that our geophones can what pick it. So, our focus in terms of practical application in real life terms is going to be on case two and what? Case three. Are we okay? That's it. So we are going to look at some situations. We are going to now focus on seismic or refraction seismology. That's going to be our focus, a very important focus. Yeah, yeah, call me what the second like 2:30. Now, if you offer. So yes, let's continue and look at refraction, refraction seismology, refraction seismology. So this is our ground surface. We have our focus. We have a geophone here, right? Then there is this boundary at this side. So there's a boundary down here. So this is layer A and this is layer B, right? Now, when we strike view, the focus, in the field we use the hammer, we strike the focus to generate waves. So when the waves is struck, the waves is going to move in several directions. Some will go this way, some will go that way, some will go this way, some will go that way, some will go this way. So several direction that the wave will go through, right? Mhm. So the wave is going to go through several directions. Let me redraw. So the wave will go through several directions. Now, here we are going to look at three possibilities. One, the wave going in this direction, the direct movement of the wave. We call it the direct wave. We call it direct wave. Then the wave will also be reflected. This is the second possibility. So this is called a reflected wave. And the third possibility is that the wave will be incident at a certain angle. And that angle is what? Critical angle, critical incident, critical angle of incident, right? So when it happens, then it's going to be It's going to move along the boundary, then at a point, it's going to what? Move up. So these are the possibilities, right? I've not drawn the um, refraction to scale, so let me redraw it. Or reflection, sorry. So let's see here and there. So in the first case, we are having the direct wave moving from here to here. That's the first case. The second case, we are having form of what? Reflection. So the angle of incidence is here, angle of reflection is also here. Then the second case, we are having the wave moving here. It got refracted along the boundary. Now, because it's refracted along the boundary, at a point, it will what? Go up through what? Reflection. Do you get it? Just as I indicated, the waves is going to vibrate this boundary, create wave front, and the wave front is going to cause the wave to move up. So these are the three possibilities. Three possibilities. Now, in the geophysics that we are doing, we want to know which of these waves will arrive at the geophones first. We call it the first arrival. The first arrival. Now, if you look with your eyes, you will see that this will arrive first, this will arrive second, and this will arrive third. But that is not done that way. There are several factors that contribute to their arrival time. Do you get it? And we are going to prove it, which of them is going to arrive first, second, third, and what last, using mathematical what expression. So we are going to look at derivation of the first arrival time. Yeah, yeah. Alfred also. All right, so we'll be looking at it briefly. So let's go to the derivation. So let me redraw things here so that it looks a little bit pretty than what I did. So I have this layer. I just want to draw it. Forgive me, it should not be that nice. Okay, I have this layer. I have these layers. This is my focus. This is my geophone. Here, I'll call this F, call this side what D, right? Then the first situation, let me use a color so that we can differentiate between them. Let me take a green. So the direct wave will go in this direction. So the direct wave will be here. This is it. Then let's look at the reflected wave will go this way and come that way. So those are reflected. It's not drawn to scale. I want to draw it at the middle. Let's see. So this will be the middle. So it's coming this way and goes that way. Come this way and goes that way. Then we have the third situation, which is like this. It goes this way, then it will come that way. So in this case, let me take this. So this is my wave. This is my wave. And let me take this to be my wave here. To be my wave here. And then the wave along the boundary, right? Now let's derive. Let's derive our parameter. So yes, assuming the distance from here to here is x, right? This is reflected wave, direct wave, and this is refracted. So I'm indicating the refracted with RE. Now I call this point A, I'm calling this point B, I'm calling this point E, right? Now we want to take the direct wave. So the first thing what we are trying to do is that we want to use time, the expression of time, to know which of these waves will get to the geophone first. So we are going to compare the direct wave. First of all, we'll compare the direct wave and the what? Reflected wave. So the direct wave is the one in green here, and the reflected is the one in blue. All right. So what is time? We know that velocity is equal to distance over time, right? And so time is equal to what? Distance over what? Velocity. So let's take the direct wave, for instance. The direct wave, let me pan to this place. So let's take the direct wave, for instance. Let's take the direct wave, for instance. So the direct wave. So the distance that the direct wave will travel is what? From F to D, right? So T for the direct wave. I'm indicating the direct wave with time. A time for the direct wave to get to the geophone. I'm representing it as T1. So the time is equal to what? FD. That's the distance over what? V what? E. Let me call this layer, sorry, layer 1, layer 2. So let me change this. Oh. So it will be what? V1. The direct wave is within layer 1, and so it's going to travel with the velocity of what? Layer 1. So we know that FD, we also know that FD is equal to what? X, right? So the direct wave is equal to what? X over what? V1. Now let's take the reflected wave, right? Now let's draw, let me redraw this portion of the reflected wave here. So it moves from here to there, right? And we are saying that this is F, this is D, and this is what? E, right? Now there's going to be a normal here, right? And there's going to be an angle here, angle of what? Angle of incidence, and this is going to be angle of refraction. Now remember, angle of incidence is equal to angle of what? Refraction, right? Now when we draw this normal, it means that this distance has been divided into 2. So this is going to be x over 2. This is going to be what? X over 3. Remember that, right? All right. Now, we want to know the time that the refracted wave, sorry, the time that the reflected wave will get to the detector or the geophone, right? Now, the reflected wave is going to travel from, the distance is going to be from F to E, and it will travel with the velocity in what? In layer 1. In layer 1, layer 2. Then from there, it will travel from E to D with also the velocity of what? Layer 1. But if you look at the orientation, if you look at this triangle, if you look at this triangle carefully, this triangle, this whole triangle carefully, because the angle here is equal to the angle here, it means that the distance F will travel, the distance the wave will travel from F to E, distance the wave will travel from F to E will be equal to the distance the wave will travel from E to D, right? And each of these distances is what? X over what? 2, right? So I can see that, sorry, not X over 2, sorry. Is equal to, so the distance that the wave will travel from F to E is equal to the distance it will travel from E to D. And so we'll see that T2 is equal to FE over V1 plus, I can replace ED with FE again, right? So FE over V2. And so T2 will be equal to 2 FE over V1. Now what is FE? If you look at this triangle here carefully, you look at this triangle here carefully, using this to be a normal, I can redraw it as this, right? I'll redraw it as this, and I'll say this is my angle of incidence, and I'll say this is x over 2, and I'll say, sorry, this is supposed to be h. The distance from layer 1 boundary to layer 2 boundary is h. So in this case, from here to here is also what? H. Sorry, I didn't indicate it initially. So the distance from this side to this side will also do what? H. And so if you look carefully, this is what? Like, this is like the hypotenuse, because this is a right angle triangle, right? And so we are looking for the hypotenuse, which is what? FE. So I will say that FE squared is equal to x over 2 what squared plus what? H what squared. Are you okay? Let me calm down a little bit. So in that case, I can say that FE will be equal to what? Square root of what? X squared over 4 plus what? H squared. Now, if I do my computation, evaluate this carefully, I'll be able to get what? X squared plus what? 4H squared over what? 4. So I can see, so I can see I'm, I'm going to get square root of what? X squared plus what? 4H squared all over what? 2. So this is my distance FE. I can bring these two here, and say 2FE is equal to a square root of what? Square root of x squared plus what? 4H what? Right? And so I can replace 2FE with this equation. So I can say this equation star, I say this equation what? 1. So I'll say put equation star into what? Into 1. So in that case, I'm going to get T time for the reflected wave to get to the geophone to be equal to square root of what? X squared plus what? 4H squared all over what? Then 1. Now, if you compare, let's try to compare something. Let me use this so that you can clearly see what we are comparing. If you compare this equation, that is the time for the direct wave to get to the geophone, and you compare the time it takes for the direct wave to get to the reflected wave to get to the geophone. Now you can see, assuming this is 0, this is for the reflected. Assuming this is 0, we are going to get our T2 to be equal to what? S squared over what? V1, which is the same as what? The direct. But here, this is not 0. This is not 0. So it means that T2 is still what? Square root of what? S squared plus what? 4H squared over V1. So it means that the reflected wave is going to get there late by this what? Factor as compared to the direct. Because the direct is going to get there earlier. If you look at the value here, x over V1, and if you look at this, if this was not supposed to be there, the time that the reflected and the direct will get there will be the same. But because we have introduced another factor of 4a squared, square root of 4a squared to the equation, it will make the time that T2 will get to the geophone increase. So it means that in comparing the reflected, in comparing the direct wave and the reflected wave, it means that the direct wave will get there before what? The, how do you call it? The what? The reflected wave. Another simple explanation to it, without even bothering to waste your time on the equation. Another thing that makes it very simple. Look at the distance. Now remember that the direct wave and the reflected wave are moving with the same velocity. They are all moving with velocity v1, because they are traveling in layer 1. And so they'll be moving in layer one with the same what velocity. Do you get it? And because they are moving in layer one with the same velocity, look at the distance that the direct wave have to take. Very short. Look at the distance they reflected. Half an hour, then it will pass here before it gets here. So the time, the distance that the reflected wave will move through the layer, do you get it? It's big, or yeah, it's bigger than that of the direct wave. And because they are traveling with the same velocity, it means that we are all traveling with the same velocity. And for me, it takes a very short distance for me to get to the place. But you, it takes a very longer distance. Do you get it? So it means that although because you are traveling with the same velocity and I'm traveling through a shorter distance, I'll reach there before you get there. So that is also another simple analogy. So in that case, in comparing who will get to the dew point first, the reflected wave is what out of the equation. So the fight between the direct wave and the reflected wave, first round, direct wave won. So direct wave will now proceed to go and meet what? The, how do you call it? The refracted wave. Now, someone will be there and be saying, hey, the refracted wave is traveling a very longer distance than the reflected. Yes, the refracted wave is traveling a very longer distance. But remember that when the refracted wave was traveling from A to B, it was traveling with a new velocity which is greater than the velocity the waves are traveling through the air. That is what will change the dynamic. So now you are going to focus on the direct wave and the refracted wave. So let's move down and that. So the first fight between direct wave versus reflected wave. This guy won. This guy lost. He's crying. That's by the way. So now we're going to look at direct wave versus refracted wave. Now we've already established the equation for the direct wave, which is x over what? V1. So let's redraw the whole setup again and let's see. So we have this. It's our due point. So this was F, this was D, this was A, and this was B. Layer 1, layer 2. The velocity here is being 1, the velocity here is being 2. Now we've already established the equation for the direct. Now we are going to look at the refracted. We're going to look at the refracted. So we want to, let me represent the time that the refracted wave will get to the choke one with what? T3. T3. With T3. Excuse me. So with T3. So let's see. We know that time and velocity and distance are related by T is equal to distance over what? Velocity, right? So first of all, the refracted wave will move from F to A, from F to A with what velocity? They are in layer 1, so velocity of layer 1. Then it will move from where? A to B, right? It will move from where? A to B. Now, in that case, there is refraction, and the refraction happens in layer 2. So the velocity there will be what? V2. Then it moves from B to D, right? And here it is reflected. It's moving in what? Layer 1. So the velocity there will be what? V1. Now, if you look carefully, the angle here is the same what? Angle here. So it means that the distance from F to A is the same as the distance from B to D. So FA is the same as what? BD. So we can rewrite this equation as T3 is equal to FA over V1 plus AB over V2 plus another FA over V1. So rearranging, I can see that, let me continue it here. I can see that T3 is equal to 2FA over V1 plus what? AB over what? 2. Now remember the distance from layer 1, the boundary of the layers is what? H, right? Now we need to get an expression. Let me calm down a little bit. Oh, it's too much. Now we need an expression. Come in. Now we need an expression for what? Let me come here for FA, and we also need an expression for AB. Now let's look. I'm going to break this down. This, I can draw my normal here going up here. My normal here also going up here. Remember the distance from here to here is still x, right? The distance from here to here is still x. Now this, let me call this G, let me call this G, right? Let's look at it. I've just created my normal, extended my, right? Now I can say, I know that FG is equal to GD. That is from here, this side. From here to here is the same as from here to here. Because the angle here and the angle here are the same, and the height here and the height here are also the same, right? So if they are equal, then I can say FG plus JD plus GG. That is this side plus this side plus this side should be equal to what? X, right? And so we also know that this and this are equal. So I can say that FG plus another FG plus GG is equal to X. So I can say 2FG plus GG is equal to X. So let's keep this equation in mind. So let's go and find FE, this distance. You know this to be what? Right angle triangle. The angle here, theta. Now, because there is refraction along the boundary, this theta or this angle is theta C, the critical angle of incidence. Critical angle of incidence. Now I want this distance F what A. I know H. Do you get it? So I have I want my hypotenuse, but I have my what? My adjacent, and I have an angle, so I can use cos. So I know that cos theta T is equal to my adjacent over my what? Hypotenuse, F what A. And so I'm looking for my hypotenuse, so F A is equal to what? F will be equal to H over what? Cos FA will be equal to H over what? Cos theta C. H over 1. So I cross multiply, right? Or, yeah, I cross multiply. Then I'm going to get this times this equal to this. But I'm looking for this. I'm looking for this. So I divide 2 by this. And that's what I had here. So that's my FA, right? So now knowing that FA is equal to what? BD. Means that BD is also what? H over what? Cos theta what? C, right? Now I need to find FG. This F and this G, right? So I know my what? My adjacent. I want my what? Opposite. So I can use what? Tan, right? So I can say that tan theta C is equal to opposite. That is FG over my adjacent H. And so I know that my FG is going to be what? H tan theta C over 1. So I cross multiply, right? So now I know my FG. Now my FG is also equal to my what? G what? B, right? Okay. So now we can find things. We can find things. We can find things. We can find things. So I know my FA. Let me use the black so that it brings clarity. I know my FA. Here is it. I can replace it here. But I don't know my AB. Now my AB is also equal to my JG. So this side is equal to this side, right? Now let's see something. We know that from this equation, we know that 2FG plus GJ is equal to X. So if I want GJ is what? X minus 2FG. But we found FG. Where is FG? This is FG. FG is this. So I can say that my GJ is equal to X minus 2H tan theta what? C. They get it? And my GJ is the same as what? AB. So now I've gotten my FE and I've also gotten my what? My AB. So I can replace it. I can replace them here. I can replace them here. Oh, sorry. My laptop is about to go off, so we'll finish with this proving, then we'll continue from there. Right? Yes, so we'll continue from there on another device. So I'm coming. Let me finish. Let me turn to this place and come here a little bit. So now that we know of these parameters, so let me start from here. So 2 times T3 is equal to what? FE is what? H over cos theta C, then 1. I've substituted is 2, right? Plus AB. AB is what? X minus what? 2H tan theta C over what? Then 2. Now I can say that T3 is equal to 2H over cos theta C V1 plus I can separate this into X over V2 minus 2H tan theta C over what? V2, right? Now I can also see that T3 is equal to what? X over V2 plus 2H over cos theta C V1 minus 2H tan what? Theta C over what? V2. Now let's see something. T3 is equal to X over V2 plus 2H over cos theta C V1 minus 2H. What is tan? Tan is sine theta C over what? Cos theta C V2. Let's come down. Let's come down and build on this equation. So I can see that T3 is equal to what? X over V2 plus 2H over cos theta c V1. So I'm factorizing 2h cos theta c V1. So I'm going to get here to be 1 minus what? V1, because V1 was not here, and we factorize it up out, and it was at denominator, it will come at numerator side. Sine what? Theta c over cos has gone out, so over what? Then what? 2. Right? Now remember the Snell's law. When the Snell's law, when we had critical angle of incidence producing a 90 degrees angle of refraction, we saw that sine theta 1 over sine 90 was equal to V1 over what? V2. So in our diagram, let me go up and show you something. In our diagram, in this diagram, you realize that, where is this thing? In this diagram, you realize that here, the refracted ray was on the boundary. And so this angle is critical angle of incidence, and the refracted angle is also 90 degrees, right? So let's come down and prove that one fast. So in that case, it means that uh, sine theta c over sine 90 is equal to V1 over V2. And so sine theta c is equal to V1 over V2, right? And so I can say that V1 is equal to V2 sine what? Theta c. I can put it here, right? So I can say that T3 is equal to x over V2 plus 2h over what? Cos theta c V1 multiplying 1 minus what? V1 is what? V2 sine theta c and times another sine theta c over what? Over V2. Have you seen that? So in this case, this will cancel this, right? So I'm going to get T3 is equal to x over V2 plus 2h over what? Cos theta c then 1 minus sine what? Squared theta c, right? Then you are not done. Then we will say that T3 is equal to x over V2 plus 2h over cos theta c V1. This in trigonometry, cos theta squared plus sine squared theta is equal to 1. And so I will say that cos squared theta equal to 1 minus sine what? Squared theta, right? So I can see that here, this whole thing is what? Cos squared theta c. And one of the theta c will cancel one of the cos theta c. So I'm going to get T3 is equal to x over V2 plus 2h cos theta c over what? Then 1. So we are going to get this equation, right? I'm going to get this equation. So yes, we'll end here because my laptop will continue on the other device, right? So yeah, I'll end the streaming here, then we'll continue on another device.